Değerli dostlar, sevgili arkadaşlar, herkese iyi akşamlar. TÜBİTAK Temel Bilimler Araştırma Enstitüsü, dünyanın en önde gelen üniversitelerinden bilim insanlarının katılımıyla düzenlediği çevrim içi seminerler serileriyle en üst düzey ve yenilikçi bilgileri ülkemizin ve dünyanın bilim ve eğitim camiasına aktarmaya devam etmektedir. Bu vesileyle yine bir güzel cuma akşamı, bu sefer kuantum bilimi ve teknoloji seminer serimiz kapsamında bir araya gelmiş bulunmaktayız. Ben de bu vesileyle hepinizi en içten dileklerimle, saygı ve sevgiyle selamlıyorum. Bu akşam yine kuantumu konuşacağız. Çünkü kuantumun sonsuz dünyasında ve insan zekasının sonsuzda olan ufkunda daha nice keşifler insanlığı beklemektedir. Hepimiz iyi biliyoruz ki maddenin yapı taşlarından biri olan elektronun yükü ve spini vardır. Ayrıca hepimiz biliyoruz ki elektron temel bir parçacıktır. Yani kompozit parçacık değildir. Şu ana kadar bildiğimiz bu. Bu yılın Mart ayında Princeton Üniversitesi'nden Profesör Phuan Ong ve arkadaşları çok önemli bir deneysel buluşa imza attılar. Aşırı kuantum rejimde bir elektronun dual, ikili özelliğe sahip olduğunu kanıtladılar. Yani iki parçacıktan sanki oluşmuştur. Biri elektrona negatif yükü veren, diğeri ise spin olarak bilinen mıknatıs benzeri bir özellikten oluşmuş gibi görünüyor. Dolayısıyla Princeton Üniversitesi'nden arkadaşlar bir elektron için spin ve yükün ayrımını deneysel olarak kanıtladılar. Bu olay yıllar önce kuantum spin sıvılarının varlığını ilk kez tahmin eden Nobel ödüllü fizikçi Philip Anderson tarafından teorik olarak öngörülmüştü. Bu akşam bunları Princeton Üniversitesi'nden dünyaca ünlü bilim insanı Profesör Doktor Phuan Ong'un rutenyum klorin 3'teki Kitaev spin sıvısının ısı transferinden kaynaklanan kuantum özellikleri konulu konuşması kapsamında dinleyeceğiz. Seminerimiz İngilizce olarak gerçekleştirilecektir. Dear Professor Phuan Ong, dear participants, dear colleagues and friends, a warm hello everyone. It is my distinct pleasure to inform you that this evening we have another wonderful episode of the inspiring online Quantum Science and Technology Seminar Series of TÜBİTAK Research Institute for Fundamental Sciences. We organize these seminars for national and international audiences with the participation of distinguished scientists and great speakers of the world. It is also my tremendous pleasure to have the privilege and honor of introducing our tonight's speaker, Professor Phuan Ong, a distinguished scientist and world-class expert in quantum science from Princeton University. He has kindly agreed to join us for this seminar, and he's going to give a great talk. Quantum properties of the Kitaev spin liquid in ruthenium chlorine 3 probed by heat transport. Phuan Ong is an American experimental physicist specializing in condensed matter physics, focusing on topological insulators, Dirac-Weil semi-metals, superconductors, and quantum spin liquids. After obtaining his PhD from the University of California, Berkeley, Ong taught at the University of Southern California for 9 years before joining the faculty at the Princeton in 1985 as a full professor. Here, in 2003, he was appointed to the Eugene Higgins Professorship of Physics, which he continues to hold today. Professor Ong has received many prizes and recognitions for his groundbreaking research in condensed matter physics, including the 2006 Kamerlingh-Ons Prize, 2014 Experimental Investigators in Quantum Materials Award from Gordon and Betty Murray Foundation, is a fellow of American Physical Society, as well as the American Academy of Arts and Sciences, the American Association of the Advancement of Sciences. He's a member of the United States National Academy of Sciences. With this, I want to invite Professor Phuan Ong to the stage to begin his talk. Phuan, good morning.
Hi, good morning.
We are very happy to have you with us. Please begin your talk.
All right, let me try to share the screen. Okay, is this better?
It's okay.
Yeah. Okay.
Yeah, it's okay.
All right. So thank you, RuCl3, for the invitation. And thank you to the audience for showing up. I know it's Saturday night when most people would prefer to be going to the movies or coffee houses. But anyway, thank you for coming. So I want to talk about some new results on spin liquids, but I understand this is a fairly unfamiliar topic, and also the audience is kind of mixed. So at RuCl3's suggestion, I have put in a lot of introductory slides to make sure that everyone can follow as much as possible what I'm going to say. Okay, so let me first introduce my collaborators. Peter Checker, Tong Gao, Max Hirschberger are all graduate students. Some have graduated. The experiments are led by Peter and Tong. And we have a close collaboration with the team from the University of Tennessee and Oak Ridge National Lab. Is my voice coming through clearly? It's okay? You can hear me, right?
It's perfect, no problem.
Yeah, okay, good.
Please can go ahead, no problem.
Yeah.
But
so
please also take a note that we have multiple choices because live stream goes through YouTube, Twitter, right, Facebook, but people are separated.
Yeah, okay.
Yeah. I forgot to.
No, I was aware of that, right? Mm-hmm. So my collaborators are Paige Lampen-Kelly, Anna Banerjee, David Mendras, Steve Negler, and YQ Yen. Okay, so this is a brief outline of my talk. I doubt I'll get to more than the first 3 items, but anyway, I'll give an introduction to from a broader perspective of what exactly is the problem, right? Why spin liquids? What are they? And why should we be interested? And then I'll introduce the Kitaev honeycomb model, which is the latest chapter in this very old topic of spin liquids. In particular, this interesting material, ruthenium trichloride. And then I'll talk about the phase diagram of this material and where the spin liquid occurs, and our new observation of oscillations. And I'll try to explain what they are and what the implications are. And then, I doubt there'll be time, but the last topic is the thermal Hall effect, which is a separate topic and perhaps maybe better left for a future occasion. Most of the results I'll mention here appeared in Nature Physics about 6 months ago. Okay, and I acknowledge funding support from the Moore Foundation, the Department of Energy, and the National Science Foundation. Okay, so to take the broad view, magnets are ubiquitous, right? They are found everywhere. In fact, I was trying to count the number of times I encountered a magnet in a 24-hour period, and it rapidly went up to 1,000. So it's the reason, of course, is that more and more increasingly, society will be going electrical, right? Everything we do will be going electrical for obvious reasons. And to change electricity to mechanical motion, which is how we benefit from the electrical power, you need magnets. So this is almost too obvious to mention, perhaps. But interestingly, I believe that magnetism in a solid was mankind's first encounter with an intrinsically quantum phenomenon. And it was mysterious 1,000 years ago, maybe 3,000 years ago. And it was mysterious until the birth of quantum mechanics, as I'll try to explain. Yeah, if the audience knows of an earlier encounter with quantum phenomenon, please bring it to my attention. So the familiar magnets, right, like we encounter in the kitchen, iron, nickel, or magnetic alloys, they become ferromagnetic at a very high temperature. So the critical temperature, which is called the Curie temperature, is of the order of 1,000 Kelvin, right, plus or minus a few hundred Kelvin. This is a very, very high energy scale in condensed matter. It's roughly about 1/10 of an electron volt, which is very high. There's another class of magnets called antiferromagnets. And these, perhaps not as familiar, are responsible for the dramatic shrinkage of hard drives, right? Hard drives, when I was a graduate student, a hard drive is the size of a textbook, a heavy textbook. But now, you know, it's the size of a wallet card. And one of the technological reasons is the role played by antiferromagnet. And then there are exotic magnetic states in solids. There are helical magnetization, spin glass, and then the topic of today's talk, spin liquids. You see that Phil Anderson actually played a foundational role in the last two topics, as he did in the topic of antiferromagnets, very early in his career. But his theoretical concepts still resonate very strongly today, as hopefully will become clear. Now, from the point of view, so these are, of course, sort of well understood from technological point of view, but for physicists, magnetic states continue to be a source of wonder and exciting research. And the reasons have to do with the following. Magnetic states are actually macroscopic signatures of strongly interacting electrons, right? So in condensed matter physics, we study many, many particles of the order of Avogadro's number. And if they are strongly interacting, our ability to understand them is quite primitive, right? Each time there's a breakthrough, the person who makes the breakthrough gets a Nobel Prize. So there aren't too many breakthroughs, but this is the dominant challenge in the field. How do you understand billions and billions of strongly interacting electrons? What are their quantum properties? And magnetic states are a very important manifestation of these properties. All right, so these are very broad statements. Let me go on to the topic of exchange. Now, a common misconception is that the reason why local moments, the spin of electrons in a metal or in an insulator align is because of the dipole forces, right? If you think of this as a magnetic dipole, it likes to be aligned with the neighboring dipole, right? If you put it in the right position. And so this is called the magnetic dipole force. That's a misconception. That magnetism has nothing to do with dipole forces. It basically is a consequence of the very intense Coulomb repulsion, as I mentioned. And Heisenberg very early recognized that. So this was perhaps one of the earliest applications of quantum mechanics to solve a long-standing mystery. So why do they align? Well, okay, by the Pauli principle, if the spins are aligned, then the orbital part of the wave function must be anti-symmetric under exchange, right? So more broadly, Pauli principle says that, you know, if you exchange both the orbital part and the spin part, the wave function must pick up a minus sign. However, if the spins are aligned, the spinners, right, alpha 1 and alpha 2 of the two electrons, alpha being the spin up, is even under exchange, and therefore the orbital part must be antisymmetric, right? So this is the manifestly written here as the difference where R1 and R2 are interchanged. But this immediately, this is what Heisenberg recognized. If you allow the two electrons to approach each other, the orbital part must vanish. And that is easily seen. If I set R1 and R2 to be nearly equal, they will vanish, right? The orbital part must vanish. So this tells me that the amplitude for finding them together is 0, provided the spins are aligned. This has amazing consequences. So that tells us that the reason that they align is because they want to minimize the chances, the probability that they will come together, right? So they stay apart, and that decreases the Coulomb repulsion energy. So that's the reason for ferromagnetism, right? So that's summarized by this statement. So when you look at a chunk of ferromagnet, like a piece of nickel, the electrons are compressed together, right? The 10 to the 23 electrons in a cubic centimeter. And if they could align their spins, they would dramatically lower their energy. And that's the reason for going ferromagnetic. And the savings is of the order of 100 millivolts per site. And this is an enormous amount of energy. And that's why the critical temperature is of the order of 1000 Kelvin, right? If dipolar forces were responsible for ferromagnetism, the Curie temperature would be below 1 Kelvin, significantly below 1 Kelvin, actually. So thank God that Heisenberg was right, because we do need ferromagnets, and they have a very high critical temperature, well above room temperature, so that they're of service to mankind. Okay, so that's the ferromagnetic state. The antiferromagnetic state comes from its exchange, and this was clarified by many of the early pioneers. Anderson, Goodenough recently got the Nobel Prize for a completely different contribution. Kanamori, Conyers-Herring, Warnier, and Néel. To understand antiferromagnetic exchange, why do the spins on adjacent magnetic ions want to become anti-aligned? One can think in the following way, right? So if the electron wave function can spread out, it will lower the kinetic energy, right? But they cannot spread out so much that they start to encroach on the neighboring magnetic ion. So they can go into the oxygen neighbor that sits in between. So this electron that spin up will leak into the oxygen site, right, half the time. And in order for it to do so, the neighboring magnetic ion must be antiparallel by the Pauli principle, right? If they were both parallel, they would violate the Pauli principle when they leak into the oxygen. So they rapidly realized that by making their spins anti-parallel, they can in fact spread out and coexist on the oxygen and then hop back again. So it was this mechanism that Anderson recognized, which he called the super exchange. Super here meaning that it takes 2 hops to get this energy calculation right. So to think of this as the electrons are confined to a small volume, and so the kinetic energy is very high. But if it could spill over, temporarily to the oxygen site, it would lower that kinetic energy. But it can only do so if the neighbors are anti-parallel in spin. Now, this actually turned out to be a very powerful theory, because most magnetic insulators are antiferromagnetic, right? So here are some examples. Now, in contrast to the previous slide, you see that the spins alternate, right? Up, down, up, down. And again, we are grateful that this thing exists because as I mentioned, hard drives would not have shrunk to the size of a wallet card without antiferromagnets. Okay, now I want to introduce the notion of a spin liquid. So to do that, so spin liquids, again, were discovered theoretically by Anderson. I need to talk about the notion of geometric frustration. Now, this is actually a familiar concept. If you ever arrange for guests to come to dinner, right? Let's say you have 7 guests coming to dinner and they sit around your table and you insist on having each male sitting between 2 female guests. And you rapidly find that with the odd number of guests, this is impossible. So this is a very familiar example of geometric frustration. You cannot satisfy this up, down, up meaning female, down meaning male, right? If you have an odd number of seats around the table. The same situation applies here, right? So there are many lattices, so I'm showing 3 examples, where if the exchange is antiferromagnetic, right, the super exchange of Anderson, and you have, then the system cannot satisfy the antiferromagnetic alignment. So here's an example. On the outer ring, right, the antiferromagnetic arrangement is happily satisfied, right? It's down, up, and so on. But the middle one is frustrated. It doesn't know whether to point up or down, right? If it pointed up, it would make the white atoms unhappy, right? But if it points down, it would make the red ones unhappy. So it doesn't know what to do. So this is an example of geometric frustration. And surprisingly, there are scores, maybe hundreds of lattices where this applies. This second example is called a kagome. I think this is a Japanese word meaning this combination, right? It's a Star of David, if you wish, on every side and then patched together. The third example is a honeycomb, which would be relevant to today's talk. This is, of course, the famous graphene lattice. And more familiarly, this is what a chicken wire looks like, right? If you ever had to roll out chicken wire in your garden, you will recognize the honeycomb lattice. So because of the geometric frustration, you can never establish long-range order, right? There can be no phase transition because the spins do not know how to align themselves. And even if you cool the temperature down to millikelvin, there will be no long-range order. However, the exchange, right, either the super exchange or the Heisenberg exchange that I mentioned, is extremely large. So this causes the spins to take on all kinds of complicated configuration in an attempt to gain energy, but yet they cannot form a long-range order. And so this sets up a very interesting situation. And Anderson proposed that this is a new state of an insulator back in 1973. I'll come to that in the next slide. So in the limit of 0 Kelvin, when it's purely quantum, it's highly frustrated. There are strong correlations between different patterns, and every spin is interacting with its neighbors, but it doesn't know which way to point. So this is a class of solids or a quantum state that is still very much unknown. For example, one doesn't know how to write down the ground state wave function, and one doesn't know what the collective excitations are. So as mentioned, Anderson proposed this theoretically as a new state of matter in the early 70s, and based on this notion of frustration. geometric frustration. Now, one way that he proposed that the spins get around this is that they form singlet bonds. So singlet bond is familiar, I think, to everyone, right? It's, you know, when you make a linear combination that's anti-symmetric between a pair of spins, right? So the pair is up-down and it has a linear combination with down-up. So this singlet bond will extend to all possible nearest neighbors or even farther afield. So the whole system then is a linear superposition of different configurations, right? So you can draw on this lattice all kinds of blue bonds in all possible combinations, and then make a linear combination of them. And that's what Anderson felt was the most reasonable approximation. But this is very, very difficult to make calculations with. Now, traditionally, physicists could deal with billions and billions of spins by adopting what's called the mean field approximation, right? You assume that the spins are all pointing in one direction, and that sets up an internal magnetic field, which then acts on every individual field, individual spin. So that's called the wise mean field solution. But here you can't, because there's no mean field, right? No direction that dominates everyone, right? So one way to guess at that was also proposed by Anderson with many of his collaborators. And that is the electron, right? Because at the end of the day, these are electrons. He proposed that the electron can be split up into what he called a spin-on. A spin-on is a fermion that has a spin half, but no charge, usually called psi, and a boson. A boson is called a holon, and it has a charge, but no spin. And this was initially a theoretical crutch, right? A desperate attempt to get the mean field. So now one can, you know, I won't go through the math. One can then focus on the charge density, right, represented by the bosons, and have them obey a mean field solution. So this is a very early attempt to force the system to have a mean field solution, not of the spins, but of the charge distribution. And some progress was made, but this was heavily criticized by many, many theorists, including Bob Laughlin. But today, this has now come back, right? This has now come back into favor, and this is called the parton representation, right? The electron breaks up into two parts, so now called parton, and one part is a boson that is charged, and another one is neutral, but is a fermion with a spin. But this is an implication, right? Because if this really happens in nature, then the neutral fermions must occupy a Fermi surface, right? And so this is implications for experiment. And the results that I will talk about will relate to this prediction. Here's a photograph of Anderson in his 96th birthday. So they couldn't put 96 candles on his cake. So they made the first approximation and put 1. So that represents 100, age of 100. But here he is, still very healthy, but unfortunately, he passed away 6 months after that, 5 months after the birthday. So that was in the 70s when Anderson discovered it theoretically. Since then, roughly 30 to 40 candidate spin liquids have been discovered. Starting in 2000s, Alexei Kitaev proposed a very interesting new direction. And he wrote down this Hamiltonian, which many of you may recognize to be the Ising model, right? An Ising model is one in which the spins can only take two positions, up and down. They aren't allowed to rotate in spin space. That is called the Heisenberg Hamiltonian. So here's an Ising Hamiltonian, but this is a very unusual kind of Ising Hamiltonian that Kitaev invented, basically. The exchange is specific to the spin direction, right? So here the spins on these sites will only point in the x direction, and their exchange energy is called Jx. So up and down now refers to the x-axis. Then the second term is a different pair of sites where the spins can point only in the y direction. And again, yeah, they have a different exchange, and similarly for the z direction. Now, this is a very strange Hamiltonian, but Kitaev found that he could solve it exactly, right? And this is highly unusual, right? It's very rare to find exact solution for a interacting system of spins or electrons. He used the device of Majoranas. I won't talk about Majoranas that much because my experiments do not really couple to them. But using Majorana representation in this colorful representation where red means a B-type Majorana and blue means the C-type Majorana. Kitaev could solve this exactly using combinations of plaquettes and so on. And knowing the exact ground state wave function, he could then calculate the excitations above the ground state. And he showed that the excitations are Majoranas and vortices. So this triggered an intense activity to search for materials that will imitate this Hamiltonian. And they were found. They were found by Jackley and Kailulin, who proposed that there are crystals that actually, to a good approximation, imitate the Kitaev Hamiltonian, plus some other terms, which I'll mention. Okay, so I will describe this more carefully in the next slide. So this is the most popular proximate. So we call these proximates to the Kitaev Hamiltonian because they're not exactly the Ising Hamiltonian that I showed. There are 2 or 3 other terms, usually called gamma terms, that nature has retained, right? But okay, so in the context of Kitaev, the 3 spin directions that I mentioned, X, Y, Z, actually protrude out of the plane. Okay, so let me step back a little bit. From the chemistry point of view, the ruthenium ions in ruthenium chloride are the magnetic ions, right? And they tend to form layers of honeycomb, a honeycomb layer. You can perhaps see, here's a layer. You can perhaps imagine this to be a honeycomb, right? Just like graphene. And then the next layer is up here, stacked and shifted a little bit into the screen. And the third layer is shifted even more, right? So the green dots are chlorine. And you see that within each layer, you basically have what's called a octahedral, which is lying on one of the faces, and they share 2 chlorine atoms. So the cartoon of this structure is shown here, right? So the spins reside on the ruthenium, and they interact ferromagnetically in the direction given by the green arrow, which is this green arrow, right? Projected down to the plane. Then the other 2 sites here interact with a different J, but the spins now point in the Z direction appropriate to this arrow, and then so on, right? The blue ones will be this arrow. Okay, so this was found to be approximate, but unfortunately there are other terms in the Hamiltonian. So when you cool it down to 0 Kelvin, it's not a spin liquid, right? So if the Kitaev Hamiltonian were exactly satisfied, we would get the spin liquid, and then we can search for Majoranas and vortices, and this would be beautiful, right? Unfortunately, nature is always more complicated than the imaginations or the limitations of the human mind. These other terms in the Hamiltonian cause it to become an antiferromagnet, a very special kind of antiferromagnet that's called the zig-zag, in which the spins actually form a chain running down what's called the zigzag axis. This is a cartoon of the honeycomb layer that I just described. So the moments on the red arrows are point right, and the moments on the blue arrows are point left. So it's zigzag. But the transition temperature is very low. You notice it's only 7 Kelvin, right? And I mentioned that iron, for example, has a transition temperature of the order of 1,000 Kelvin. So this is a very feeble antiferromagnetic state. And not surprisingly, perhaps if you apply a magnetic field in the plane, this is the honeycomb plane, parallel to the zigzag axis, that's A, you kill the ordered state, right? So to repeat, nature has these remaining terms that prevent you from achieving the Kitaev spin liquid. Instead, you get an antiferromagnet. You can kill the antiferromagnetic state by applying a field roughly comparable to the critical temperature, right? 1 Tesla is roughly 1 Kelvin. So 7 Tesla field will kill the magnetic order. And it's widely believed that the state above 7 Tesla is a quantum spin liquid. Okay, so this material does become a spin liquid after all. Perhaps not what Kitaev imagined, but the nature of this spin liquid is now extremely interesting for all kinds of experimentalists. Now, you cannot increase the field too high, because when you do that, every moment, right, let me go back to the routine, right? If you imagine applying a field in this direction to your right, all the moments now, because of the Zeeman energy, will then align with the field, right? So instead of a spin liquid, you will get a trivial polarized state, which is uninteresting, right? So as I've shown here, I call it a paramagnetic state, but maybe more accurately, this should be called the polarized state. But anyway, there's this interval here that is very interesting. And before our experiments, in fact, a group in Kyoto, led by Matsuda, claimed that when they performed the thermal Hall conductivity, kappa xy, I will describe this later on, the thermal Hall effect, the conductivity corresponding to the thermal Hall effect, becomes quantized, exactly the way that Kitaev had predicted from his zero field theory. So this increased the intense interest by quite a bit. And we thought that we should check this result, right? Because it is so amazing that even though the Kitaev solution is at the end of the day not appropriate because of the high field, that his prediction on the quantization of the Hall conductivity is observed by the group in Kyoto. Maybe I should pause to invite questions before I launch into the experiment. Does anyone have questions that I can? Everything's good? Okay.
Yes, it's okay.
All right, so let me push on.
Let me check some. Yes, please continue.
Okay, so this is perhaps unnecessary. This is how we actually do the experiment. And the tiny crystal here shown in black, this black slab is the crystal. And all these gold wires are bonded to the crystal, and they are attached to thermometers. So here's a thermometer. And that's how we measure the temperatures at different points of the crystal's edge. Here's another crystal, perhaps clearer, and you can see the gold wires that connect to the edge of the crystal, and the other end is connected to a thermometer. And then we apply a heater, apply a current to a heater. The heater then conducts heat down this crystal and onto the bath. So this big blob here is the bath, right? So this is a cartoon representation. The heater pumps heat current down the crystal to the bath, and the various thermometers on the edge will detect measurements of the temperature. And we measure temperature to accuracy of 10 microkelvin. So these are extremely sensitive and very well calibrated thermometers that allow us to distinguish a microkelvin or 10 microkelvin at an ambient temperature of a few Kelvin, right? So we are measuring things to 1 part in 10 to the 5th resolution. Let me skip over this and come back to these slides, to these mathematical expressions, if time permits. It's roughly to emphasize that, if you're familiar with the electrical Hall effect, maybe I should say that. If you're familiar with the electrical Hall effect and the Hall resistivity, J will correspond to electrical charge density, charge current, sorry. And kappa corresponds to sigma, the tensor sigma, and the gradient of temperature corresponds to the electric field, right? So from elementary electrodynamics, J, right, the current density is the sigma tensor multiplied, or the matrix multiplied into the electric field components. Here it's just the same thing. It's just a thermal analog. So just like in electrical conductivity, you can back out the conductivity by inverting the matrix, right? You actually measure the voltage in electrical measurements and infer the conductivity, right? So by measuring the voltage changes, you infer corresponds to the electrical resistivity, rho, and then you invert the matrix to get the conductivity. Okay, this is a fairly technical point, but important for this field. So here's our surprising observation. Let me step back a little bit. So we apply the heater current to drive a heat current down the crystal, and we measure the temperature drop, right? So the temperature difference between A and B will be a measure of kappa XX. So the diagonal components of this matrix is called kappa XX. That is completely analogous to sigma in electrical measurements, the conductivity, right? So I'm reporting in the next slide the value of the conductivity when you apply a current vertically going to the heat bath in a magnetic field that is pointed parallel to the current. I hope that's clear. So I'm reporting the conductivity along the X direction. And the magnetic field, as mentioned, is parallel to the zigzag axis. Why? Well, because that's the direction that we can kill the zigzag state, as I mentioned, right? So we are right here at very low temperature at 1 Kelvin, and we are increasing the field until we kill the antiferromagnetic order. And then now we're into this interesting phase called the quantum spin liquid, right? And we monitor how well the crystal conducts heat, right? That's what the conductivity kappa measures, right? How well does it conduct heat? So this has been studied before. In fact, one of my former postdocs had reported these measurements about 3-4 years before. And what people had seen was this black curve, right? The thermal conductivity as a function of field drops in anticipation of the suppression of the zigzag state around 7 Tesla, right? That's right here. And then now when you enter the spin liquid, it just increases and doesn't seem to be doing anything interesting, right? But really, when you cool the temperature down below 4 Kelvin, you see that it's doing a lot of stuff, right? In fact, it's showing very dramatic oscillations. And these oscillations, to us, look very much like Landau quantum oscillations, which I will explain in a couple of slides. They get larger and larger as you cool the temperature down. So we are going from 4 Kelvin down to 0.7, and then pushing further, we are going down to 1 Kelvin, right? 0.96 is 1 Kelvin, down to half a Kelvin. And you can see that when you get down to our base temperature of half a Kelvin, the oscillations are almost 50 to 60% of the total magnitude. And this is peculiar, it's shocking, because heat is conducted by spin excitations and the phonons, right? You recall that phonons of the quanta of vibrations of a crystal, and spin excitations are, for example, spin waves or magnons, that's the standard name. But neither magnons or phonons should show this regularity. They shouldn't oscillate with field, and least of all have this very specific temperature dependence. So Peter, who was the student who discovered this effect, when he brought it to our attention, my first advice was that repeat the damn experiment and get rid of it because it should not be there, right? But Peter measured several crystals together with Tong Gao and verified that it was real. So we are presented with a new finding that is completely perpendicular to common wisdom, right? To the received wisdom of the field. And so it's something to really sit and worry about. So here are a few pertinent facts. The amplitude of the oscillations are largest within the interesting quantum spin liquid state. Okay, so remember the interesting state is right here in orange, between 7 and 11 Tesla. That's 7 Tesla here and 11 Teslas here. So they get whopping big in oscillations, but they do penetrate into the zigzag state in a very highly suppressed form. So you see they continue to ring right down to 4 Tesla, then they abruptly vanish. Okay, so again here you see that between 7 and 11, you can see very large oscillations. Above 11 Tesla, they abruptly vanish. So when you enter the trivial state, when they are fully polarized, nothing happens, right? The oscillations die abruptly. You can see that this is a plateau. So nothing happens. In fact, other groups in Germany have pushed these measurements to very high, 20, 30 Tesla, and it's all completely flat. So everything that's interesting happens below this crossover to the trivial state. And the phenomenon is most spectacular in the quantum spin liquid state. But they do penetrate as a weak oscillation into the zigzag state, as I mentioned. Okay, so we sat on this for about a year before writing it up. And here are 2 different samples, 1 and 3. Okay, so again, in reference to the phase diagram, remember the 7 Tesla field is where you kill the zigzag state. And then here's the interesting quantum spin liquid. And then at 11.5 Tesla, you kill the quantum spin liquid, right? And you notice that the amplitude, which is represented by the orange patch, is a maximum in the quantum spin liquid, and it dies abruptly when you get into the polarized state. It survives as a tiny little finger when you go into the zigzag phase. Sample 3 is even more dramatic. It has a huge amplitude, right? So the measurement is on the right hand here. So it's 0.1 in these units. And here it's like a 0.01 in these units. Sorry, Peter switched the units between these two diagrams. But anyway, it's something like a 7 times larger here. And now we understand why. We know that the cleaner you make the crystal, the larger is the amplitude. And this is exactly what Landau oscillations would predict. How do we know the sample 3 is cleaner? Well, we look at the plateau. So the oscillations die out, but they leave behind this plateau, which is actually a godsend, because this is nature's way of telling us how clean is your crystal. Because here, the thermal conductivity is dominated by phonons, and phonons are very sensitive to disorder in the lattice, because they will scatter off the disorder, and that will degrade the thermal conductivity. So the magnitude of this plateau, let's say at a benchmark 1 Kelvin, is a very good measure of how clean your crystal is. So look at the magnitude here. Let's see. Okay, it's on the left now. It's roughly 2.3, 2.4. Whereas for this particular crystal, sorry, I have to go back. Yeah, so sample 1 is this crystal. At 1 Kelvin, it's only 0.7, right, in the same units. So between the two crystals, the plateau is 0.7, and here it's 2. So this is 3 times cleaner. That's what the phonons are reporting to us. And the amplitude is 7 times more intense. So that was very comforting that the 2 different crystals show roughly the same behavior, except that the amplitude is much more dramatic. So when we submitted this, okay, so before I talk about that, let me make a sidebar discussion of what Landau oscillations are. So this is textbook material. My apologies if this is all familiar to you, but since this is a broad audience, maybe I should remind what the pertinent facts are. If this were a metal will have a Fermi surface that's a sphere, let's say, for some simplicity, right? So that's the characteristic signature of a metal. The electrons all occupy a Fermi surface in momentum space, K space. When you have a magnetic field, there is a characteristic length, right? You notice that you can form this combination, Planck's constant divided by charge and field. This defines a particular length. And this length is extremely important in quantum materials. Anyway, okay, so once you apply a field, this whole Fermi surface is destroyed by the field. What remains are orbits that have the same radius of all these radii that match one of the cylinders will be allowed, right? Everything else is disallowed, right? So all the orbits will have a radius that matches one of the cylinders. And this is Landau quantization. So why is that? So when Landau proposed this, it wasn't quite well. Okay, so I'm going to explain this using modern terms as follows. I think this would be easier to understand. So any circular orbit in momentum space is translated into a real space circular orbit, right? So if a circle in K space becomes a circle in real space, where we live. The translation is given by this. So the radius in real space is the radius in K space, K, multiplied by the square of the magnetic length. So you can imagine an electron living in this white orbit will execute a circular orbit in blue in real space. And so here's the quantization. This orbit must enclose an integer number of flux quanta. A flux quantum, I think I show it here, is again just Planck's constant divided by E. These are the units of flux, right, in quantum mechanics. Why does this have to be an integer? Well, because as the electron goes around, its wave function, the phase of the wave function will rotate. And for every flux quantum, it must rotate by 2 pi. Right? This is, of course, just the Bohr-Sommerfeld quantization. So I've shown this by the phase clock. So the phase clock has to wind and come back to 2 pi for every flux quantum, right? So if there are 6, as shown here, it must wind 6 times and always come back to exactly the same value. Otherwise, the wave function becomes multi-valued, and that's not allowed. So you can see that because of this constraint, not all orbits will satisfy that. Only very few discrete set will satisfy that, and they are identified to be Landau levels. So hopefully, this Bohr-Sommerfeld quantization scheme will help you understand why it is that Landau levels appear. Now, when you vary the field, the radii of the cylinders will expand, and therefore the number of levels will decrease. And that leads to oscillations, right? So these are the Landau quantization induced oscillations, and they affect everything that you measure in the metal, right? Whether you're measuring magnetization, resistivity, heat capacity, everything, every macroscopic observable will oscillate with magnetic field with exactly this period. So hopefully this reminds you what Landau oscillations are. And now back to the data, you see that these look like Landau oscillations, and we think they are, because all the analysis that I will show next says that yes, they are Landau oscillations. The awkward contradiction is that there are no electrons whatsoever, no free electrons, sorry, in this insulator. The energy gap is 2 electron volts, and you can rapidly do the math, right? 2 electron volts in a Maxwell-Boltzmann activation expression means that it's e to the minus 20,000 when you get to 1 Kelvin. So all thermally activated electrons are extremely exponentially suppressed. There are absolutely 0 electrons in the material, yet it's imitating Landau oscillations. So this is an observation that was extremely difficult to publish. And it took us 2 years, so we sent it to Nature, and took us 2 years to fight with the referees, but in the end, they just refused to approve publication. It's just too crazy and too bizarre to be true, right? But that's exactly what we look for as experimentalists. We want to go against the grain. We want to push against the boundary. We want to push at the noses of theorists to show that, you know, they don't understand what we are seeing. Anyway, so we made sure that this is real and not just some measurement artifact. So we look at many samples. I will just show data from 3. So the plots here, let me first focus on the blue and the red. So the blue and the red each represent the extrema, right? Extrema of the oscillations obtained from the derivative, plotted versus 1/h. This is the signature of the Landau oscillations. And they indeed vary like 1/h. And the 2 crystals, one in red, one in blue, actually match each other very well within the experimental uncertainty. And then for one of the crystals, we tilted the magnetic field at the angles here, theta, right, shown here. When you tilt the magnetic field out of the plane, they actually follow the same track, provided you plot the A component. You plot the component of the tilted field parallel to the A-axis. And you see that they more or less match. The displacement in the vertical direction is just for clarity, right? So it's just an artificial displacement. So with these 5 sets of data, you show that we convinced ourselves that these are intrinsic and not an artifact. So here I mentioned that here's the puzzlement, right? The oscillations mimic Landau levels, but there are no free electrons, right, to the magnitude of 10 to the minus 20,000, because the gap is too EV. The gap is very well studied by photo emission. We can also deduce a Fermi surface, even though there's no free electrons, and in units of Tesla, there are the numbers shown. Let's see, what's the next slide? Let me skip over this. Okay, so here's how we deduce the previous plot. We can take the derivative of these curves, and the peaks of the derivatives, the peaks and the troughs, will tell us the period. And those are the data points we plotted. And as I mentioned, the blue and the red dots represent 2 different samples, and they track each other very well. Here's a plot where we do not plot the integer versus 1 over h, but rather versus h. This was to satisfy one of the referees that this is not periodic. When you plot it versus the field itself, it's not periodic. In fact, it insists on 1 over h as the periodicity. And that is a quantum signature, right? Because of the Landau quantization that I explained, the 1 over h periodicity is truly a quantum signature, because that's an area in K space, not in real space. Oh, okay. So I had mentioned this. I already mentioned. So I'll quickly go through it. So to explain the difference in the amplitude, we recognize that the purity of the crystal lattice is extremely important. So I mentioned this plateau value for the phonon conductance, right? So we are harnessing the phonons to tell us how clean the crystal is, right? So this is our way of telling future experimentalists how to observe these oscillations. They should take the crystal. The first thing they should measure is go to 1 Kelvin, measure the longitudinal conductivity, the magnitude. If the magnitude doesn't fall into these values, then the oscillations will be heavily suppressed, right? So hopefully this will help people to detect the oscillations. But for the present purpose, we found that the cleaner the crystal is, the stronger the oscillations. So this summarizes the finding. The oscillations are periodic in 1 over h, except for a break in slope at 7 Tesla. This is when the zigzag antiferromagnetic state is suppressed by the field. So for some not understood reason, it causes the Fermi surface cross-section to shrink, to expand rather. So this invites a Landau level interpretation, but there aren't any free electrons around. So if you wish, it's pushing you to the conclusion that we are seeing neutral fermions occupying a Fermi surface. I didn't talk about this A-axis component. It's very reproducible, and we are convinced this is an intrinsic effect. The amplitude is largest, this I did mention, when you are in this strip of interval that is the quantum spin liquid. It abruptly vanishes when you exceed it into the trivial polarized state, at high fields, but a weak tail persists into the ordered phase. And this suggests to us that the ordered phase is actually mixed. It's a first order transition to a mixed phase where the spin liquid still survives, but now is a minority phase in this mixed phase system. The zigzag phase rapidly dominates as the field decreases. They damp out above 4 Kelvin, exactly like in semi-metals. And the quality of the lattice is extremely important, right? The cleaner the lattice, the higher the amplitude. Again, just like in semi-metals. So as mentioned, the favorite approach now. So today, right, 30, 40 years now, let's see, it's been, wow, it's been almost 50 years since Anderson's first paper on spin liquids. Now, this is a very fashionable topic in modern quantum matter, because it's one of the recognizable quantum states that have no theoretical insight. All the theorists are puzzled, and they are trying to smash down the door, right, by a battering ram. But this is now re-emerged. Remember, I mentioned the parton representation, treating the electron as made up of a field. Now we're into field theory, right? Into a field psi that describes neutral fermions and a field describing charged bosons, right? So one can write down the Lagrangian of these two fields, and the electron destruction operator is the product of the destruction operators for the spinon, the fermion, and the charge boson. But because of this, the two fields actually interact very strongly by an internal vector gauge, right? Because at the end of the day, the electron is, recognizes that these two particles must interact very strongly. They must come together. So this attraction is described by an internal vector gauge. And this vector gauge gives rise to an internal field, which many theorists, several groups, propose this internal field is actually Landau quantizing the neutral Fermi surface, right? Because once you propose a neutral Fermi surface, you are immediately confronted by the absence of the Lorentz force, right? How could a neutral particle be deflected, right? Be deflected by the conventional Lorentz force. A neutral charge doesn't care about the V cross B force, right? So it must be a different kind of magnetic field, and the current thinking is that it arises from the curl in momentum space of this internal magnetic field. Well, these are early days, but this is a very useful direction to think about. Okay, how much time do I have left?
So 5 minutes, is it enough?
Yeah, I'll quickly march through this. Okay, yeah, sure. Okay, so not to belabor the topic too much, I will just talk about the interesting report by the Kyoto group. So it's led by.
So anyway, you can take more. I just say 5 minutes. If you want,
yeah, shouldn't be more than
feel
5.
free.
Okay,
Please feel free.
Shouldn't be more than 5 minutes.
Yeah.
Yeah. So Yuji Matsuda was a former postdoc of mine many years ago, 30 years ago, perhaps. And they had found that, if you, the same material, right? If you now drive a heat current down the crystal, as shown by this red arrow, and you can measure the transverse difference in temperature between the right edge and the left edge. And they found that there indeed, so this would constitute a thermal Hall conductivity, right? Just like the electrical conductivity, pretend that you're driving a charge current down the crystal in a magnetic field. if you see a voltage difference between left and right edges, that would constitute a Hall effect, a electrical Hall effect. Here it's the thermal analog. So seeing that effect is already surprising, but even more surprising is their claim that it's quantized, that it takes on a specific value exactly equal to a quantized value. I didn't write it down. Perhaps you can read this. Yeah, it's somewhere here. So it's only given by universal constants, right? Oh, here as well. Sorry, I should have written this down. Exactly as predicted by Kitaev, in terms of Boltzmann's constant, Planck's constant, and yeah. So this was a shocking finding, and so obviously invited a lot of people to measure it. So I want to say a little bit, well, maybe I should skip this in view of the time. There's a very interesting mirror symmetry regarding the thermal Hall effect, which I hope to talk about here, but maybe this is not, regarding the time, this is not, I shouldn't do that. Anyway, we confirm that there indeed is a thermal Hall effect in agreement with Matsuda. So here's the raw signal. So the raw signal, so think of this in the electrical case as the voltage. So this would be the Hall voltage. And you see that when you sweep the magnetic field right along this axis, when it's negative, the signal is negative, and then it's almost zero, and then it's positive when the field is positive. That's a bona fide Hall signal. But it's very strange because the field is parallel to the current, right? And there should be no, so there should be no Lorentz force for two reasons, two independent reasons. One is that the spin excitations are neutral, and two, the field is parallel to the current, so there's no V cross B term. Nonetheless, the signal is there, and these are early data of ours. We show that translated into kappa xy. So this is the thermal analog of sigma xy, the famous Hall effect. It's very temperature dependent and doesn't agree with any quantization that was reported by Matsuda's group. So recently we have made this into a very careful and detailed study. So we have measured this thermal Hall signal. So here's a cartoon that Peter drew. The heater is here. You're driving a current vertically down, right? That's the thermal current. And you're measuring the temperatures on both sides to excruciatingly high resolution. And you can see that the signal is very weak, but we can actually see it, right? And it has a very systematic dependence on temperature. So the various curves are taken at fixed temperature, for example, at 9 Kelvin versus magnetic field. And then the computer changes to a different temperature. So each of these curves takes about 10 hours. So the way it's done is that my students lock up the lab at midnight, set the computer program going, come back next morning, and the computer puts out this data, right? So it's all under automated control, and the temperature is maintained to extremely high resolution. But then you can convert this data into the kappa xy. So this is equivalent in the Hall electrical channel to going from rho yx to sigma xy. I hope that's, yeah, you remember that. Once you express it in kappa xy, the curves never cross. So it's a very systematic dependence. And there's no evidence for quantization. I think the dashed line here is the quantized value. And so you see that it's very temperature dependent. Okay, so from all these measurements, you can build up what's called a color map. And this shows the variation of the Hall resistivity, thermal Hall resistivity, according to this scale bar. Red means large, and blue or orange, green means 0, right? So it's 0 over everywhere except this narrow region. And interestingly, it's finite over this spin liquid window. Then it goes negative, that's blue, negative over a very narrow patch. So it's a signal that seems to know about the spin liquid, but it survives to very high temperature where it's very large. In the end, we convince ourselves, I will not go through the theory, we convince ourselves that this is actually caused by a spin wave packet that runs around the edge, right? Unlike the oscillation signal that I mentioned before, which is from the bulk, these are specific to an edge channel. Now, many of you are aware of the quantum Hall effect. It's the same thing, right? The quantum Hall effect is a wave packet of electrons that exists on the edge. So this is the thermal analog. And the way the thermal Hall effect arises, once you have a wave packet hugging the edge, if you apply a heater, say to the bottom, this edge will be warmer. And if they are controlled by the Bose-Einstein distribution, they will be heavily occupied. So you have a huge transverse Hall thermal current going to your right compared with the one near the bath, which is cooler, right? So this unbalance is exactly what gives you the Hall effect, right? So hopefully this is apparent. When you reverse the field, the circulation reverses because something called the Berry curvature. This is a very hot topic today in the context of topological materials. The Berry curvature will reverse in magnetic field. Now, we are sure this is right because it fits the theory very well. So this is shown by the black curve, and as opposed to the quantization results, which requires a fermion excitation. So clearly it's not fermionic, it's bosonic, but it also fits the edge description very well. And that, of course, alone is not sufficient. It fits it over all fields that we have measured. And from these fits, we can extract two quantities. One is the magnitude of the spin excitation mode that gives rise to the wave packet. And it agrees very well with electron spin resonance experiments. So we find comfort in this agreement that we are actually measuring a quantity that has already been reported in the literature, seen by completely different techniques, right? This is electron spin resonance. And secondly, the magnitude gives you a Chern number of 1. I didn't describe this, but in all topological materials, which ruthenium chloride is, the Chern number is a measure of the Berry curvature winding number. Yeah, sorry. So these topics are too modern for me to talk about in the context of this general talk. If you imagine going back to K space, the Brillouin zone, if the K space has a Berry curvature in the Brillouin zone, and you take a line integral around the Brillouin zone, right, and you end up with a winding number of 1, that would be the Chern number. But sometimes it can have a winding number of 2, 3, and so on, right? So the Chern number is the winding number of the line integral of the Berry curvature. So the fact that we are seeing the integer to be 1, right, rather than something like a million or 1,000 or 0.1, this also gives us comfort that we indeed have captured the true nature of the thermal Hall effect. Okay, so with this, perhaps I should end the talk and summarize as follows, right? I talked about observation of a very strange phenomenon, totally unexpected, quantum oscillations that mimic Landau quantization, usually called Shubnikov de Haas, and it's possible evidence for neutral fermions in the quantum spin liquid phase. Now, this is such a jarring conclusion that I think the theoretical community, which now is quite familiar with our findings, is very averse to accepting. So this remains to be seen. We are sure that the experiment is right. And so whatever the interpretation is bound to open some new window into the quantum spin liquid phase. Then I also talk about a separate phenomenon, and that is the thermal Hall effect. So we feel that these are actually boson edge modes, and the inferred, sorry, this shouldn't be a gap, spin excitation is in excellent agreement with electron spin resonance. Moreover, it yields a Chern number of 1. So sorry to go over time. I hope this has been of interest to all of you, and I'll be happy to take questions. Thank you.
Thank you very much for this very deep and exciting talk. Now we can pass to questions. Please ask questions or send them. Yeah, Oğuz Gülseren. Just a minute. Oğuz hocamızın sesini açalım lütfen. Ben açamıyorum.
Hello, can you hear me?
Yeah. Yeah, please, Oğuz hocam, please.
Thank you, Professor Ong. I have a couple of questions after this very interesting talk. Okay, I'm completely convinced with this Landau quantization from this experimental evidence, but I'm trying to follow. Still, you are doing a thermal conductivity measurement. So this is a heat current. Then in the paramagnetic phase, I mean, if I start from that, I can understand, I can describe everything in terms of the phonons. Then you enter this quantum liquid state and the zigzag phase. And apparently we have this Landau quantization. But still, we have the same quantity, thermal conductivity. So what is the mechanism there? What is the quasi-particle? So apparently, something new, not the phonons.
No one really knows. So what's the question?
And do we have some quasi-particle that describe this thermal current in this quantum liquid state?
So we believe that phonons are still present, but they interact very strongly with the spin excitations, right? So spin excitations in the high field regime above 11.5 Tesla would be the familiar magnons, right? So, so they are not interesting, but they, as you go into the quantum spin liquid, they have a multi-magnon, if you want to use that language, multi-magnon configuration. This is what the electron spin resonance tells us. So they are a many body states of magnons. And some people say they are signatures of Majoranas, but we don't know. We don't know what they are. But they presumably carry a good fraction of the thermal conductivity. And it is their quantization that is giving rise to the oscillations that we are seeing.
Okay. Maybe can I have another quick question?
Sure.
So are these two-dimensional materials or bulk materials?
So it depends on which theory you subscribe to. At first blush, they are two-dimensional, right? Because they are layered, and in terms of they are van der Waal materials, very easy to cleave, right? So from the electronic point of view, they are two-dimensional. However, from the magnetic point of view, and this is information from neutron scattering, the magnetic excitations are three-dimensional. So they have significant dispersion along the c-axis. So it's not clear whether the magnetic description can be just purely two-dimensional. So some theorists think of the Fermi surface as basically three-dimensional Dirac pockets. Right, so it's known, right, just like in graphene, the Fermi surface of the neutral excitations are Dirac-like, and they sit at the K points of the Brillouin zone, right? So, so some theories think of them as Dirac ellipsoid, but interestingly, the ellipsoid is not along the c-axis, the long axis. It's not along the c-axis, but rather tilted in the plane. So you see then how that naturally gives rise to magnetic oscillations with the field in the plane. Yes. But honestly, no one really knows, because it's very hard to derive the many-body state from looking at conventional tools like neutron scattering and spin resonance, right? Because these are many-body excitations.
So does anybody try a system like chrome iodide? So it's similar structure to
that's an interesting question. Yeah.
Magnetism study that, but yeah.
We were exploring other variants of this, icosahedral edge-sharing materials. I'm not sure chromium iodide has that. So it has to be octahedra that share edge, right? Just like in, and there are many such.
From the hexagonal corners and the iodine just sticking out.
Yeah, so they may not, but that's an interesting, if very clean crystals become available, we will certainly take a look.
Thank you.
Sure.
So thank you. Phuan, there's a question in chat. Can you see this, or shall I read for you?
Let me go to my chat. Is there a relation with the phonon conductivity and the fractal structure of the lattice? The lattice doesn't have a fractal structure, sorry. So not sure what you mean by fractal, but the lattice is just one of the regular Bravais-Lau, classification. And the phonon conductivity I've discussed, right? At very high fields, 13 Tesla, it's purely phononic at 1 Kelvin, or nearly so, nearly purely phononic. Then as you decrease in field, magnons first come in, and then the magnons change into this strange magnetic excitation that has no easy description. So, but phonons are always there, right? So, but they strongly interact with the spins. Does the phonon transport always obey Brownian motion? No. The phonons are very ballistic. The crystal lattice is very clean, so it's not Brownian motion. The phonons travel for a good mean-free path. They are actually obeying Boltzmann equation, but with very long mean-free paths until they scatter off the spin excitation. Are there cases for the Levy flight? I see. So this has to do with diffusion motion. No, I don't think Levy flight applies here, but maybe I'm not sure. I'm not sure what aspect of Levy flight you're referring to. The phonons are very long-lived in the clean crystals, and to the extent that they scatter from the spin excitations.
Thank you. Phuan, may I ask maybe final questions?
Sure. Yeah.
Having read your last paper on these topics, I was very excited, and looking at comments as well, I noted that this spin-on and boson separation, which you state that is very rigid, may have very, very exciting applications. For instance, in quantum computing technologies. Can you please comment on this?
Well, so this is looking well ahead, 20, 30 years from now. So right now, of course, as you know, the schemes for doing quantum computing are all based on what we call physics of the 1970s. They're all based on superconducting qubits, right? So, and they, especially the Sycamore quantum computer at Google and the rival one at IBM. These are all based on conventional BCS superconductors, and they are extremely fragile. So these experiments are all run at 10 millikelvin.
Mm-hmm.
And the hope is that by going to topological materials, the robustness of the many body states will be automatically protected. So topological quantum computing may have maybe the way to go, except the challenge is extremely difficult. It's very intimidating. But what is the nature of that? So if you could, for example, you could take two Majorana excitations, and you could braid them by forcing them to exchange repeatedly. Then in their whirl line, right, when you look at the whirl line of these two Majoranas, they will form a braid, right? And because the whirl lines cannot untangle in the face of weak perturbations, this will capture quantum information, right? How many times did you braid them? That the quantum information will be much more resistive to perturbation, to destruction, unlike the qubits that are currently being used. But of course, one has to find Majoranas first, right? And even though the recent experiments from Kovenhoven's lab, the ones from Amsterdam, have now been called into question, many people believe that they are real, the Majoranas. So that's one example. The other example is anyons. Anyons are particles in the fractional quantum Hall state, first proposed by Bob Laughlin, that do not obey fermion or boson statistics. Instead, they obey 1/3 statistics, 1/3 or 2/3. What does that mean? So you think of fermions, when you interchange them, they pick up a -1, right? So this was the Pauli principle that I mentioned in the very beginning. For bosons, when you interchange them, they pick up a phase of 2 pi, of 1, right? So fermions are pi in the phase rotation, bosons are 2 pi, but anyons are 2 pi over 3, which is a fraction, right? A third of a 2 pi rotation. And for the last 30 years, experimentalists thought that Laughlin was just, just theoretical construction, right? But nature is very peculiar. Whatever the human mind can imagine, nature will always implement. And now we know from experiments happening in the last year that anyons are real. People have now actually gone in and measured their phases, and they indeed come out to be the 2 pi over 3. So the particular experiment I have in mind are the ones performed in France. Forget the group's name, but anyway, they inject 2 anion beams in a 2-dimensional gallium arsenide crystal. They inject 2 anion beams and cause them to scatter, right? If they were fermions, the scattered products, the channels will be different, right? Because fermions intensely dislike each other, so they will separate out into separate channels. If they were bosons, they would scatter into the same channel, right? What they find for the Laughlin anyons, they do the fractional scattering, which means that the 2-particle correlation is consistent with this 2 pi over 3 statistics. So once I saw this paper appear, I was convinced that these anyons are real. So nature, whatever the human mind can imagine, and if it's successful in explaining one thing, nature will carry out the implementation. So I think with all these glimmerings of fractional statistics, topological excitations, I think the coming 2 decades will be very exciting as physicists and chemists explore all these properties and become comfortable with pushing them around, exploiting them. We may see a new generation of devices based on fractional statistics. And this, of course, has huge implications for quantum computing.
Thank you so much once again for this very exciting talk. That was great pleasure to listen to you this evening. Can you please make final remarks if you want?
Well, I think those are my final remarks. That I think these are exciting times to get into the field of quantum matter, quantum condensed matter, it used to be that when I first arrived in Princeton, of course is a hotbed of cosmology and particle physics. So when I first arrived here on campus in '85, I had to hide my interest. I had to not talk so much about my interests. But things have changed so much, in the last 30, 40 years. We have seen the rise of quantum phenomena, quantum materials. So I often tell my students this is the second quantum revolution. Now we understand the basic principles of quantum mechanics rather well, and even have glimmerings of approximations for truly interacting systems. We can now explore the second quantum revolution. This is how to harness truly quantum effects to achieve experiments that will benefit mankind. Right? So, one can imagine a whole slew of beyond quantum computing, right? Whole slew of devices that exploit applications that we haven't imagined, we haven't thought of. Right?
That's
So
exactly.
for example, if we take an electron and we rotate it by 2 pi, right? We think that the electron is still the same, right? But it's not, right? You have to rotate it by 4 pi, right? So this is well known to everyone. But what if we could have a device or a crystal where this becomes manifest, right? We rotate the crystal by 2 pi. It's not in the same quantum state. You have to go 4 pi to return it. Now, of course, you say, well, there's no such thing. That's because of decoherence at the human level. But if it were like a magnet where all the electrons doing the same thing without decoherence, this may be achievable. So it's such devices that may, be in our future. So this is pretty exciting. Yeah, so those are my remarks.
Thank you so much. Thank you so much. So we can close our session here, thanking everybody also who participated in this very exciting talk. So bye.
Thanks for the invitation. Bye.